We did a few of these kind where we're just analyzing particle motion left and right. It's not really a related rate. It kind of goes back to, well, of course, when you see dy or dx dt or whatever, you know you're doing an implicit derivative. So it goes back to that. But also the idea of acceleration and velocity being the same sign, that kind of stuff. How do we know when a particle moves right? Positive velocity. Okay. And same if we said maybe it's moving up, it would be positive velocity. And then left would be negative velocity or down. First thing we need to do is take the derivative or turn this into a differential. So this is product rule. So f prime g, which is, I'm going to write it y dx dt just to keep the y out front. And then f g prime. And derivative of 18 is 0. Okay, right now we know dy dt and we know y. That's it. And that leaves too many variables. So what else can we do to plug in stuff that we can leave to solve? Yeah, so if we take this and we plug in that y is 6, then we can see that at that point x is 3. Okay? And now we have enough information to plug in everything except for dx dt, and then we can solve for it. So we're going to get 6, and then I'll just leave that. 6 dx dt plus 3 times 8, not 2, equals 0. Okay. And then just divide, and we'll get dx dt is negative 4. Okay, so x representing the position on this hyperbola. You guys remember what a hyperbola is, by the way?
Like an extreme situation. That's a good way of putting it. I was about to say that too.
Okay, hyperbola, if you cut the two cones and you end up with something like this, right? As a cross section, remember that? That's a hyperbola. Okay. You guys took pre-calc, right?
Yeah, we didn't.
I don't remember. Yeah, that was not.
All right, so we should have chosen A. It's the rate of x, the rate of change of x with respect to time is negative. And so we're moving left or decreasing, maybe we'd say.
The record shows.
Okay. Limit as x approaches 0, sine x over x. What is that? 1. That's something you should have memorized by now. Limit as x approaches 0, 1 minus cosine x over x is 0. Okay. Limit as x approaches infinity of this rational function, rational-ish function. Nope. These do not matter. Right? When we consider infinity, we don't care about the 3 and 5. So be careful in your notation, but those two don't play a role as we go to infinity. Then we have to ask which of those two grows faster. The bottom, so that is also 0. Okay, how'd you do? You had 4 answers. Hold up, how many you got correct? Hold them up. How many did you get correct out of 4? Okay. 3 of them should have been pretty fast. The one above, maybe. Hopefully you're getting there on those kind. All right, let's check. Do you want to do beacon or cone first?
Cone.
Cone, okay. I would take good notes if you didn't get this. Please don't just follow and be like, oh, I get it, and I'll be able to do it, because you won't. Okay? Write it down, write it out. If you got it, that's awesome. I'm going to clean this up just a little just because it's, well, maybe I'll just make it smaller. But Friday, by the way, Friday Friday was an off day for me, and so I understand everybody has those, but I, I was not clicking on all cylinders on Friday. So hopefully that didn't mess anybody up. But I want to add something to this. I didn't want to give it away on Friday, but now we need it for our work. So when you do these kind cone ones, are in particular this way, I'll have to think about other ones that have this kind of relationship, but basically you have to note that the relationship between the radius and the height stays constant as we fill this tank or drain it if this is a draining problem. And that ends up being pretty critical to solve the problem. So keep an eye out for relationships that are constant relationships like that. And so I said that on Friday, but didn't write it as an equation, which is fine. I wanted you to think of that. So I'm going to write that here now, where we can say R is 1/2 of H. That relationship stays constant all the way up and down. Okay? And then you need, because we're doing a rate problem, we can also say dr dt is what? 1/2 dH dt. Okay? So we'll probably, not probably, I'm going to just tell you, we're going to need both of those things in the problem. Okay. So we have our specific picture already drawn, and I think that's probably sufficient. I would probably list what some of these other numbers are. So we see at the rate of 5 cubic feet per second, let's label that. What is that? Or per minute, excuse me. What do we label that in our problem? 5 cubic feet per minute. That is dV dt. Okay. The tank has a height of 6 feet and a radius is 3. That was given in the picture. What is the rate at which the height of the water level is rising when the water is 2 feet deep? So if we follow our steps, step 2, our goal is what? What's our goal? What are we finding? dH dt. Okay, this one related the variables for us, which is always nice. So we have our equation. And again, this is just a constant relationship in a cone for the volume of a cone. So it's not a differential yet. So step 4 is to take the derivative. And this is another one where I would put the constant out front. And now we have the product rule. Well, product and a couple other things. Okay, so this is f prime g. So we need to do 2r and then dr dt. That's all f prime. 2r dr dt is all f prime. And then g is just h. Plus, now we're doing the second function. This is now f g prime. So f g prime. And we're good. Any questions on the derivative? These can be a little intimidating because they start to look a little bit like crazy, like stuff everywhere, right? All right, let's just pause here and look at what we know, because step 5 is evaluate at the point, at that moment. Well, we know dV dt, we marked it up there. These are constants. We know a radius. We don't know dr dt. And we don't know a value of a radius, but we can plug it in those things up there that we wrote down. Okay, and we know h. So that leaves this one, the dH dt, for something to solve, if that makes sense. Yeah. Well, we don't have dr dt as a number, but we have dr dt as an expression that goes back to dH dt. Okay? So as long as we can eliminate that variable, even if it's in terms of another known one, that's okay. Or another one we're solving for, excuse me. So let's go plug all our stuff in. Actually, you can plug it in here, or you can rearrange first and then plug in. Which do you guys like to do?
Rearrange.
I personally would plug in. Remember we said along the way, plug in as soon as possible.
I was just
You were pranking. dv dt said it was 5. And then 1/3 pi. 2, and we don't know r, but we know that it's half of the height. And we don't know dr dt, but we know that it's half of dh dt. And then we have h plus, again, we have 1/2 h whole thing squared as a substitute expression for the radius. And then dh dt again. This kind of problem is definitely an FRQ. So what do you need to do as you work through FRQs? Go slow, take your time, be careful, right? I should say be deliberate, be careful, that kind of thing. Right. Am I in your way or something? Okay, let's clean up stuff and then we'll start trying to isolate dH dt. And what I mean is like this whole chunk right here has h's in it and some numbers that we can mess with. Same over here on the right. So this is where you can get lost in the details and make mistakes, so be careful. Here's what I see. 2 and times 1/4 is what? Or you could just say 2 times 1/2 times 1/2.
1/2.
1/2, and then we have h times h.
H squared.
Okay, so this becomes 1/2 h squared, and then dh dt.
We don't plug in the 2 for h.
You could, I guess. I'm not going to, but you could. Okay, over here, 1/2 h squared is just 1/4. 1/2 quantity h squared is 1/4 h squared. dH dt. Okay, we've seen this kind of strategy before. When we want to solve for something like dH dt, what do we do with it? We can factor it out, right? It's part of both of those terms in the brackets, so factor it out. I'm having trouble writing. Let's see if I can fix that. Okay, so we got that factored out. And let's go ahead and continue. We want to get dH dt by itself. You could plug that in now if you want. What's 1/2 plus 1/4, since those are like terms?
3/4.
How are we going to get rid? Yes, you're right. How are we going to get rid of 1/3 pi? Also, we need to get rid of that. Yeah, or multiply by the reciprocal, right? So tell me if you're okay if we do this. So 3/pi times 5. Are you good if we do that? On the left side, I mean. Okay. And then we said this is 3/4 h squared dH dt. Okay. Still good? Maybe I'll just show this real quick. Times 3/pi. And cancel that. Okay. 3/4 h squared, we can just divide, which is going to cancel the 3. Uh-oh. I heard a sigh.
I forgot to do.
Okay. Very good.
Yeah.
All right, we finally got dH dt isolated in the whole left side we know. Note on this that the 3's cancel, the 4 comes up to the numerator. So what does this become? 20 over pi h squared, I think. Do I look right?
Yeah.
And then plug in, we have h was 2. And I like my answers like this. So that is 5 over pi. And we better label. What's the label? Okay, but we're finding the change of the height as we fill this tank up. So cubic feet is a volume. Good job. Say it. Feet per minute. Okay. All right, so now that you've worked through it, how do you feel that you did? Yeah.
Can you just simplify this a lot earlier by finding the radius?
We can't find the radius.
It's probably not the height. The current height is 2, so it's 1.
I wonder if I agree with you.
That's what I did.
Did you get 5 over pi?
I messed up after that, but it was way simpler than the rest of that.
Okay. Let's see back here, if you're saying 1, so we'd still have to keep dr dt. I'm looking back right here. So if we plugged in, I kind of like doing it symbolically, and you're going to find that that's how I do my math. And then plug in at the end. So if you guys don't like that, tell me and I'll try to adapt. But I've always liked the algebra side of it too. So let's see. Can you guys do this without me rewriting? So this is 2 times 2 is 4. And then, yeah, I'm going to have to write it out. Because dr dt is still in terms of, maybe I should have plugged it in one step below. Okay. Are you guys good if we take a moment to check that?
Yes.
Okay. So I'm going to kind of combine what I wrote as step 4 and 5 a little bit. So you guys check me as we go. 2 times 1, and then that's still going to be 1/2 dH dt times 2 plus 1/2 times 2 is just 1. So plus dH dt. All right, let's simplify this whole junk mess. 2 times 1/2 times 2 is just 2. That's going to look weird when I pull that out, but oh well. Okay, this 2 plus 1 will cancel that 3. Yeah, it works.
Hey.
Okay, so the moral of that story is
Plug in.
maybe it's easier for you if you plug in as soon as you can. Then you miss out on all that other good stuff. Come on, guys. All right. Since we're talking about a time test, plug in. Now, I will tell you, and I don't know where you want to write this, but this is what I want you to write someplace. Don't plug in before you do your derivative. So maybe I don't know where it's good. Maybe up here. This is where I would go if I was you studying these problems. But you guys pick a good spot. I'll write it twice. Yeah, just definitely don't do that because that would throw off things. Don't plug in before the derivative. Ryder, good job. Yes.
We're a batch of smart individuals. I believe for the rest of our course, we should create a way to shrink you and then clone you so that you're on our shoulder during the test so you can on every question.
Okay.
Yeah.
That'd be funny.
Because who studies, right? That'd be easier than studying. Probably.
Would it?
Yeah. Shrinking you and cloning you.
Shrinking and can you clone me and then shrink me so I can stay the same size?
Then we would have to shrink you simultaneously.
Yeah,
No?
Oh, we shrink the clone and then clone the shrink.
Yeah.
The clone.
Yeah.
Oh.
I thought you said you were a bunch of smart people. Good job. All right. Beacon problem. This one's kind of cool. This is how I see it, and you might see it differently because I helped a few people at lunch who all three saw it differently than me. For some reason, this is where I go with it. So follow along on this. The circle represents the beacon. Okay, I don't know what we're looking at here. Like, I'm thinking of it, you know, like the sweeping light out at the airport. That's how I'm thinking of it. Like it's shining as it goes around. Okay. It tells us that this is 2 miles from 2 miles out in the water. And it says, let A be the point that is closest to the beacon, which tells us that that's a right angle. Okay, that little line doesn't say it explicitly, but that's what it means, or at least that's part of the result. Okay, the beacon rotates at 10 revolutions per minute. So D, B, I don't know what you want to call it, for the beacon, is rotating at 10 revolutions per minute. But we don't have any calculus that does revolutions per minute. You know what I mean by that? Like when things are turning or sweeping through an angle, what do we measure that in? Radians, right? So how many radians per minute, that's what we need this in. We need it in radians per minute, is 10 revolutions. 20. How many radians are in one full turn? 2 pi, right? So 2 pi. And then we do this 10 times per minute. So this is 20 pi. And then if you want to label it, just so you know, it's 20 pi radians per minute. The radians actually doesn't matter in this one, but we have to be in radians for it to work. I'm just saying that we're not going to use the units in any labels. Okay, so if you think about that light out at the airport, and it's sweeping across, or you could just think of it like if I have a flashlight and I turn, I'm going to shine different parts of the wall or something, right? It's the same concept. So it didn't tell us if this is turning clockwise or counterclockwise. You see that it, for some reason for me, I'm just interpreting it as counterclockwise. And so down here, maybe not quite there, at some point, it's shining 2 miles away from the point closest to A, okay? So what did we just end up creating in our picture? A right triangle, okay? All right, well, let's do step 2, which says, how fast is the point where the beam hits the shore moving? Okay, I would probably call this, just because we have been, the x direction and the y direction. So what are we trying to find? What is our goal? If I had a good flashlight, I wish I did, I would just stand here and we could watch it trace left to right along the wall, right, as I turn.
I have a good flashlight.
You do?
Yeah, it's not with me. It's up in the You're running. Go get it. It's up in the
Hey, I might actually have a laser pointer.
Is it DX?
See if I still have it.
I don't really get that.
Does it still work? Hey, sweet.
Do you ever come with Trevor?
Hey, look at me, Trevor.
Do it. I
Right,
can
so
set-
that's our shore over there, okay? And we're saying how fast does it go, right? Well, what is the dimension in our...
It's DX.
Ronan, jump in front of the laser and then sue it.
Okay, right there is straight in front of me, so that's the point where I wrote the right angle. And it's coming along here. At some point right there, it's 2 miles from the point straight in front of me. So we're saying dx dt, that's what we're searching for, right? That's our goal, I mean.
Very good show. Why do you have
I don't remember. I think I actually bought it for this. Yeah, I'm pretty sure I bought it for the squishy part on the other side that writes on tech. What's that called? A stylus, kind of? Do you remember COVID and we had to teach from home?
You didn't use it to blame?
Yeah, back
No, I didn't say that. All right, anyway. That's our picture, that's our goal. Now we need a relationship that relates what we know. So step 3, what relates this angle and the 2 sides? That's what we're looking for. We have to have the angle because we're told the rate of change of the angle. Otherwise, we might be able to use the Pythagorean theorem if this was all just a length thing. But since it's an angle, a rotation angle, we have to bring trig into it. So which trig ratio relates those 3 pieces? Those right there. It's tangent, opposite over adjacent. Remember that? Okay. So tangent of theta equals x over y. That's our general relationship. That's always true for this scenario. And then we need to take the differential of this. So what's the derivative of tangent of theta with respect to time? Secant squared theta. Is that all? Because this is just the derivative of tangent, right? Now we have to do the inside, which is derivative of theta. So d theta dt. Guys, when you do your equation, you start seeing pieces that you're told. That's a good sign. By the way, I'm going to change this b. I did d beacon, but now I'm going to change it to theta since we named the angle theta. Okay, so d theta dt. What I'm saying right now is, hey, I see that I have that piece as part of my derivative, and I was given that piece. That's kind of a check on your work. All right, how about this other side? Both of these are being differentiated rather with respect to time. No. X and y. Well, y is a constant, but not x, right? So we need to take the derivative of both, and then we can say that y is a constant. Yeah. Yeah, quotient rule. So remember, quotient rule is low d high minus high d low. That is an ugly minus sign. Over low squared. Remember the quotient rule? Okay, so derivative of, so low d high would be y dx dt. And then high d low would be x dy dt. And then all over y squared. Everybody good? Okay. I would note at this point, probably in my work, dy dt is 0 because that point is not changing. That beacon is fixed out there in the water. So this whole term goes away, which is super nice. Now we could simplify that. The y over y squared becomes just y in the denominator. We're trying to find dx dt. We know d theta dt. We know y. We do not know theta. How do we get theta? At the moment that our picture is taking place right here, where it's 2 miles, let's call it 2 miles west maybe, and 2 miles out north to the sea. How do we get theta at that very moment?
Inverse tangent?
Yeah, I would just set up a quick trig ratio since it's a right triangle. So opposite over adjacent, 2 over 2. What is the angle for when tangent is 1? That's really what we're saying. Good job. So you need to have these memorized, remember? We'll have to keep reviewing the unit circle, but this is at pi over 4. Okay? Yeah?
And the one in the,
What?
I'll say it in a second, I'll definitely go there.
Okay, here's what I'm saying.
Nobody else.
It's that point right there when the sine and the cosine are the same value. Okay, that's pi over 4.
Oh, and 5 pi.
Oh, you were trying to think of another one? Okay,
Yeah, sorry.
gotcha.
My brain was fine.
All right, step 5 then. So secant squared of pi over 4. D, let's just plug that in. What was that? 20 pi times 20 pi for d theta dt. Y is 2. So is dx dt over 2. And the reason I'm doing that again, y over y squared is just y in the denominator. So save a little bit of work. Okay, can you do anything with this? We have pi's and we have 4's. Can I simplify that at all? Yes or no? No, because one of them's inside of the secant squared, right? Okay, so this is, I don't know secant squared because I can just do this. 1 over cosine squared of pi over 4 times 40 pi. So I just multiplied the 2 over. Okay, now we need to figure out, hold on. Huh? What is cosine of pi over 4?
2 pi. Root 2 over.
Let me shrink this and move it somewhere else.
Was that right? Root 2 over 2.
Okay, so this is 1 over root 2 over 2 squared times 40 pi. All right. So this is what, 2 over 4, right? In the denominator. So if it's 2 over 4 in the denominator, it's 4 over 2 in the numerator. And we get 80 pi. What do we label that? Miles per minute. This thing is moving.
Holy cow. That is a lot. That is
Okay, did anybody get it? At your work at home? I'll give you this little reminder that we have done problems now where we have used Pythagorean theorem relationships in a triangle and now tangent or trig. So beware that you might need both. How do you know the difference? Like when would you use trig versus Pythagorean theorem?
Like distance versus speed.
Okay, well, speed could still be distance change over time.
angle values versus touch.
Yeah, like if you're given something that's turning and that's an angle change, that's going to be the trig version. And if you're just given distance changes, then it's going to be the Pythagorean theorem. All right. I'm going to give you one more to try tonight. It's this one in your packet. The Ferris wheel one. Please try that. Maybe I'll just show you the answer. We'll maybe talk through it briefly, and then we need to move on to our last two topics. We'll probably just get through one tomorrow, and then I don't know. Okay. Also, don't stop listening. So you're gonna do this Ferris wheel one, and then I'm gonna assign a personal project progress check, MCQ and FRQ for review for your test. I'll probably hand it out. I don't know. I haven't decided if I want in class or at home, but we'll need to start that Thursday. Okay? Yeah. So study. Do the progress checks that I assign on AP Classroom.
You said start it and then take it.